All right, so we're going to be talking about group theory and Yang-Mills theory today. And you can read what's obviously what's in Schwartz's chapter. I'm going to depart from it quite a bit. Yeah, we're going to depart from it. So, let me start by saying I'm running out of this chalk that I actually like, so I guess I'll switch to the normal chalk. So, the first thing is that many theories are invariant under global unitary transformations. That is to say, psi I prime of x equals uij psi j of x, sum j equals 1 to n, however many fields you happen to have. And this is true particularly if the matrix is unitary, and of course, if that would be what then? An n by n unitary matrix. But of course, an n by n unitary matrix is an element of a group called un. So there's a group called un is the group of all n by n unitary matrices. It obviously forms a group because since the matrix is unitary, the adjoint is the inverse, and the product of any two unitary matrices is itself unitary because u1, u2 adjoint is u2 adjoint, u1 adjoint, and consequently that's the inverse because u2 adjoint, u1 adjoint times u1, u2 is just the identity. So u1, u2 is unitary itself. So these things form a group, and as you know, there are many matrix groups. One set is the unitary matrices. Another set is the unitary matrices that have determinant 1. These are said to be, these form the group SUN. And the reason why people, well, let's just, all right, let me skip that tangent for the moment. All right, what Yang and Mills did is they figured out a way to make an action that's invariant under local transformations. That is to say, where psi I of x was sum on j from 1 to n, u I j of x psi j of x. Now, you've probably seen me go through this rain dance several times, but it's so important that I think it's something I should repeat because it's of essential importance. It's easy for the mass terms, or for things that depend on psi dagger psi to be invariant, because if you have m psi dagger psi, or let us say m squared, so let's think of these as scalar fields for the moment. We'll talk about Dirac fields later. But if you have m psi dagger psi, well, this is m squared, I mean. You have a sum I equals 1 to n psi I star psi I of x, then this is invariant. This is invariant also under a local transformation, because this would simply be, or rather, let me just put a prime on it. say that the prime value is m squared sum now ijk u star ik of x psi k star of x uij of x psi j of x. And I like to use the term, the star. In fact, I almost always use star to mean complex conjugate if it's a number, Hermitian adjoint if it's an operator. And then I reserve dagger for where you call a moving company to take the vertical thing and make it a row. All right, well. Trying to get all the mileage I can out of people's jokes. Okay, so this is clearly m squared sum ijk psi k star u dagger. Well, u ik star is u dagger ki. So that's another meaning for dagger. I also use dagger for adjoint, especially on matrices. It really makes more sense on matrices. X uij x psi j of x. And this all works because we're always talking about the same x. So this is just u dagger u, which is the identity. And so this is m squared sum ijk psi k star x delta kj psi j of x. And then, so that's just m squared psi dagger psi. So the parts that don't involve derivatives are just as they're invariant when you make a local transformation, for the same reason that these ones are invariant when you make a global transformation. And it's because with something that just involves the fields and not their space-time derivatives, we're always talking about the same x point. But when you have derivatives, you have different x points, and then it was necessary for some cleverness. Now, of course, this cleverness had already really been done by various mathematicians, and in particular it had been used by Einstein in creating general relativity. But it wasn't being used in physics, and in fact, when Gang and Mills introduced it, I suppose people noticed, but they didn't notice very much because it was thought to be a curiosity for quite a while, actually. So let me say what they did. What they wanted to do was to do something with di of x so that something like that would transform the same way psi transforms, which is to say, psi transforms by being multiplied by u. In other words, psi prime of x is u of x, psi of x. Where now I'm going to be using matrix notation for a while, and that's so much easier. So what they did was they added an extra term. They said d psi plus a psi. Well, that they're going to call d psi, and in fact, let's put in a mu here. So that was basically their real insight, and then what they realized was that what they needed was that this structure here transformed the same way that psi transforms. So in other words, they want d mu psi prime to be u d mu psi. which is the same thing as psi, which is similar to psi prime as u of x psi. And it's funny, once you realize that that's the problem, or at least that this is a plausible solution, a possible solution, or something to try, then it's pretty easy to figure out what's going to happen. Because what you do is you just write this down. Well, that's d mu plus a prime mu times psi prime. I'm going to leave out the x. Well, that's of course the essential thing. Psi is an n vector, so this is an n by n matrix. And there's an n by n identity matrix here that I've suppressed. And so this is d mu psi prime, and this is u d mu psi. So we want this to work out, and let's just multiply it out. Well, this is, of course, d mu plus a prime mu u psi, and this is u d mu plus a mu psi. And now it's pretty clear what's happening. You've got d mu on u times psi plus u d mu psi plus a prime mu u psi equals u d mu psi plus u a mu psi. Okay, well that's reasonably simple, right? In fact, you've got two terms you can cancel. So we get rid of this term, and we get rid of this term. And then we have an equation of the form. This is a Coleman form. d mu u plus a prime mu u minus u a mu psi equal to 0. And a simple way of satisfying that equation is to say that, well, we're going to have the parenthesis equal to 0. So we're going to say, in other words, that a prime mu times u is going to be u a mu minus d mu u. And now we can turn that into an equation for a mu prime. If we just multiply from the right by u adjoint, and so that gives us a mu prime is equal to u a mu, u adjoint minus d mu u adjoint. Okay. Any questions at all? All right. This is the part that's it's important to understand what we've done so far. Now you can know those. Let's notice, however, there's a trick that's worth knowing, and this trick shows up many, many times. It shows up in general relativity, and it shows up here in Yang-Mills theory. 1 is equal to u dagger. Duh. So if we differentiate both sides, we get 0 is equal to d mu u adjoint plus u d mu u adjoint. And of course, when I'm writing here d mu, let me just make absolutely plain, just in case. This means d by dx upper mu. Okay, that's what we're talking about when we say mu. Okay, well here, this says something funny here. This says d mu u adjoint is minus u d mu u adjoint. So this, where did this come from, this stroke?
You're going to do the,
Huh?
yeah, the parentheses around the,
Oh, yes, thank you. Yeah, well, they're kind of funny parentheses, though, aren't they? There. Okay, so in view of this, we can also write this as u a mu u adjoint plus u d mu u adjoint. And that's sort of a nicer form because you get rid of a, you have two advantages here. One, you get rid of the minus sign, and my brain can't cope with minus signs. And secondly, you have a derivative that acts on the last term, and so you don't need the damn parentheses that I screwed up over here. All right. So this is a nicer form. All right. Okay, now let's turn to, let's look at this covariant derivative again and think about how it's transforming. So the basic idea was d prime mu psi prime is d prime mu u psi, which is, and we want that to be u d mu psi. So in effect, d mu prime u is u d mu. There's this funny sort of relationship here. And if we write this out explicitly, what we have is d mu plus a prime mu u is u d mu plus a mu. Okay. And let me rewrite this another way, which will make you feel a little better, I think. Because you see, you've got this derivative here that's not acting on anything, so you may wonder what's going on. How can this be the same as that? Well, I'm going to rewrite the left-hand side. It's going to be d mu u plus u d mu. In other words, I'm looking at the left-hand side and the right-hand side as differential operators. And this is of this form, plus a prime u equals u d mu plus u a mu. So these two terms cancel again, and we get back the usual expression, d mu u plus a prime mu u is u a mu. So that's the basic relation. But that's the same, in other words, that's the same thing as this. But, so another way of looking at this is saying that d mu prime is equal to u d mu u adjoint. All right? And so let me just demythologize this also. This is d mu plus a mu prime is u d mu u adjoint plus u a mu u adjoint. And okay, this d mu though is still alive, and so there's another term here. There's also u adjoint d mu, and this term cancels that term because this is the same thing as the identity times d mu, and this is the identity times d mu. Okay. So this is a perfectly real equation that d mu prime is u d mu u adjoint. Something about nomenclature. when Yang and Mills introduced this thing, this derivative transforms how? It transforms covariantly. That is to say, it transforms as u d mu u adjoint. Okay. So this is said to be the covariant derivative. And I'm putting quotes around it because in general relativity, covariant derivatives are a little bit, it's a somewhat different term. It's similar, but not exactly the same. But in physics, we're just sort of, in other words, in the particle physics end of the field as opposed to the GR field, we're a little more sloppy. Yes?
Can we start again? Okay, you had me up till the middle line there. Yeah, so, okay, so du prime psi prime, and then that becomes u, the psi prime becomes u psi. Okay, what happened there? How do we go from there to there?
Oh, we need this to be true.
Oh, we need this to be true.
Yes. Of course, I can't spell want.
Okay. So it's not necessarily that you did a step to get from the middle to the right.
Right. That's the whole thing that happened over here, you see. In other words, we said we wanted d mu psi prime to be u d mu psi.
Okay. Okay.
And because then you see, and now of course I should have said why. Well, because then, just as psi dagger psi is invariant, so too if you have something like d mu psi dagger, d mu psi, then this would be invariant. Okay? Because this, yeah, I should have said this. This would then be d mu psi dagger u d mu psi.
Okay.
Okay, that's the key point. Of course, I missed it. Let me give you a candid bringing this up.
Okay.
So that's the whole point. The reason why Yang and Mills introduced this was because they wanted the derivative to transform like the field. The vector of derivatives to transform like the field, like the vector of fields. And to get that to happen, they changed what they meant by derivative in such a way as to have this to work. And in fact, so it does work. Now, any other questions?
So, can I back you up one more step?
Yeah.
And that,
yeah, I mean, this is the part that, as I said, I mean, I don't think any of us needs to know all of the details of all of the trace relations and so forth. Okay, what are you asking?
so yeah, so why isn't there a prime on the du prime in the transfer space?
Point me where you're talking.
Okay, so first, okay, you go down one, so you have an a prime. So why is
well, there's no change in the ordinary space derivative. You're not changing space-time.
Okay, so there's no metric to go from one
No,
space
we're
to
not,
another
this is not general relativity. This is just,
space. Okay.
we think about flat space, okay?
Okay. Okay.
But yeah, that's a good question. In GR, you are changing flat space.
Okay.
I mean, you change that. You're dealing with arbitrary transformations of the coordinates. And so you're changing the coordinates. Okay, so what we've got is this covariant derivative, and it transforms in this covariant way. And the reason it transforms that way is that after we cancel the two extra terms and just have this thing act there, then we see this is just the transformation of the matrix of gauge fields. This matrix of gauge fields, by the way, will normally be written this way. A mu will be I times the sum, some generators. I somehow call everything A. I once was taking abstract algebra at Southbourne College, and on an exam, I constructed a proof by setting A equal to 3 different things. Got a 0 for that problem. Perfectly clear to me what I was doing, but I hadn't noticed that I used the letter A for 3 separate quantities. Anyway. So these will be n by n matrices. So this will be some A equals however many generators there are. And let me just use a capital N for the moment. And the TAs are n by n matrices. And in fact, there'll be Hermitian matrices because the group is unitary. And so, so that's what we'll actually do. But let me go on with the abstract part here. Once we have the d mu transforms this way, we can see that the commutator of d mu with d nu prime will of course be d mu prime, d nu prime, and this will be u d mu u adjoint, u d nu u adjoint, and so this is going to be u d mu u adjoint u d nu u adjoint minus u d nu u adjoint u adjoint. Now, of course, that is 1 and that is 1. So this is equal to, so in other words, d nu prime is then u times d mu d nu minus d nu u adjoint, which of course is u d nu adjoint. So, what that means then is that we have a way of making the gauge field, of course this A mu isn't called a gauge field. I like to call it a gauge field even though it's a matrix. It's actually a matrix of gauge fields, or several gauge fields. So for SU2 there are 3 of them. For SU3 there are 8 of them. And for practical purposes that's all you need to know. But of course there is more to it. All right, but this allows us to make a gauge, something that's invariant. So in fact, what you do is you define F mu nu to be simply this commutator. And notice that when you do that, the free derivatives cancel. So this, when you multiply this out, you don't have any extra derivatives there. In other words, F mu nu is no longer a differential operator. thing, matrix. And so what is f mu nu prime? Well, this, of course, will be u, f mu nu, adjoint. So it has nice transformation properties. In fact, it says it transforms covariantly in the jargon of particle physics, which is oblivious to jargon of general relativity, which is perhaps just as well. But anyway, to make this thing invariant, what we do is we take the trace, and you can tell this is quantum class because trace is the same as h bar, which is equal to 1. All right, trace of f prime mu nu, f prime mu nu, this thing is invariant. And why? Because it's the trace of u, f mu nu, u adjoint, u, f mu nu, u adjoint. And so we've got these guys that turn into just the identity. And then you know the trace is cyclic. That is, the trace of AB is the same as trace of BA. So we take this U and put it at the end, then U dagger U is 1. So this is the trace of F mu. Okay, so what we've got then is an action for the gauge fields that's invariant. And I showed you that if the size or scalar fields, we had a simple action that's invariant. I should back, so let me quickly find the Dirac's action just to show you that this is also invariant. In this case, we would have psi bar gamma mu, say, d mu plus m psi, and let's put a prime on that. Well, what is it going to be? It's going to be psi bar u adjoint gamma mu d mu prime. Let me use this expression, u d mu u adjoint. And so this is u d mu u adjoint plus m psi prime is u psi. And now you see everything cancels. U adjoint u adjoint u, and the m just has u adjoint u. And so this is psi bar gamma mu d mu plus m psi. Okay, so this is so Dirac's action is invariant. This is Dirac's action in Weinberg's notation with Schwarz's notation of next line. All right, let me go back. Any questions? All right, let me say something about forms, and also let me put this out as a funny kind of homework problem, although this isn't the sort of homework. This is more like this is more a blue sky problem than a homework problem. But before I get to that, let me explain what we're doing here. Okay, so let me just say something about forms. Or one form. Let me just say, the form notation is very cute. Okay, it is really, really nice. Okay, so here's a one form. And if things, if we're just doing E and M, in other words, in abelian theory, so that this A is either just a field, a single field and not a matrix, or it's in a matrix that multiplies the identity, then what you have is A squared would be A nu, dx mu, dx nu. And the rule with forms is that dx mu, dx nu, people often write a caret here to indicate that this is an anti-symmetric product. So this thing, A mu and A nu commute, and these anti-commute, and so this thing is 0 for the abelian case. Abelian, of course, just means that the group, all the elements of the group commute with each other. That's an abelian group. All right, so the idea with these forms is that dx mu minus dx nu dx mu. That's basically the picture. And now, one of the cute things about forms is that if you're talking about abelian gauge theory, in other words, like electrodynamics, you can say the Maxwell tensor is just dA, where D is something that's particularly simple. It's just, actually, I've forgotten what the name is. I'll show you what it does, though. D on A is D on A mu dx mu. So that is partial x mu, partial x nu, dx nu wedge dx mu. So it's this exterior derivative, that's what it's called. All right. So now you see, because these are anti-symmetric, this can be rewritten as 1/2 dA mu dx nu minus dA nu dx mu times dx nu wedge dx mu. And so this is 1/2 f nu mu dx nu wedge dx mu. So in other words, what's really cool about this form, one of the things that's cool about the form notation is that when you're dealing with classical electrodynamics or any abelian gauge theory, you can say that F is dA. Okay. And there's something else that's fun or cool. Namely, d squared is just identically 0. The square of the exterior derivative is 0. And that's because if you have dd any sort of a form at all, and let me write it as a one form then. Let's just say ai dxi. So then what is that? D, and this would be dj ai dxj wedge dxi, and then this would be dk dj ai dx, actually these are upper indices, dxk wedge dxj wedge dxi. And the point is, these two guys are symmetric, k and j. These two guys are anti-symmetric, so the whole thing is 0. And so that's the big trick of the method of the form people is that you just often wind up with things that you have a symmetric thing times an anti-symmetric thing, and so it's automatically 0. And okay. Now here's, all right, so here's the homework problem. Yeah. The homework problem is that when you go from abelian to non-abelian theories, you no longer, I'm sorry, I skipped something. Inasmuch as d squared is 0, and the Maxwell tensor is d exterior derivative of the one form, you have that 0 is df, because that's dga. And this is two of Maxwell's equations. So the homogeneous Maxwell equations come out like that. So that's one of the really cool things. On the other hand, this gets loused up in non-abelian theory, and the homework problem is for you guys to straighten it out. And or alternatively, to do some kind of a web search, you know, and see, has anybody figured out how to do this? The normal solution is, well, we just say f is dA plus a squared. Remember, a squared is 0 if you're talking about an abelian structure. This a, by the way, is called a connection. That is to say, this structure here, the generators times the gauge fields times I, summed over all the generators, is called a connection. Anyway, back here, so you say f is the exterior derivative of the connection plus the square of the connection. And this turns out to be right. And in fact, I can show you why. But the homework problem is, you know, to somehow understand this. Why? Not why it gives the right answer, but you see over here, for the abelian case, you have something called the exterior derivative, and it's obviously an essential part of the formalism, and so you say D on the one form gives you the Maxwell tensor. Well, duh, what are we doing here? In other words, there's something going on, I don't know what it is. Yeah?
So D on the one form gives you a 2 form, and I'm
Yeah.
adding another 2 form to this, so this seems kind of like you can do a derivative.
Well, it's
on
not
something and add a
wrong.
constant. No, I know, but there's a kind of abstract analogy to if you do a derivative and add a constant or something. Or
Is that from the connection?
Yeah, you know,
like
in
a
a
gauge
sense,
tensor, it's similar in a sense to that.
In a sense, yeah.
Because you're adding an arbitrary.
You may be right, because in a sense, what are we doing? We're saying d
It's
plus
D of A squared.
d plus a on a. That's what we're doing, aren't we?
So you're shifting.
Covariant, yeah.
Huh?
That's a covariant, yeah.
That's what?
Yeah, so this is like a new exterior.
You're saying it's essentially, it's like the covariant derivative.
Yeah. So
Like,
this
where
is
are you
covariant
finding?
exterior derivative, right?
In other words, it's,
It's,
yeah, I mean, this is the covariant derivative, and,
It's the same.
yeah, all right,
It is
so.
the same thing. Just plug in that. Plug in the definition.
but that's just a very
Okay, so,
abstract.
yeah, you guys may have done a marvelous, I owe you candy.
Okay.
Maybe what we should do is just say big D is little d plus a, which is sort of what you were saying, and what you were saying. Well, it certainly works. So then we say, then the Yang-Mills 2 form is big D on A. I don't think we have d squared equals 0, but I mean, I don't think we do, conceivably. All right, anyway, let's see why this is the thing that I previously wrote as a commutator of 2 covariant derivatives. And let me use Roman letters rather than Greek letters. So then f is dA plus a squared. So what is that? That's di ak. Maybe I should do this in two steps. dxi, in fact, let me drop the carets, okay? All right. Okay, so that's what this is. And so we can rewrite this as 1/2 di, taking advantage of the anti-symmetry of these, diak minus dkai plus ai ak dxi dxk, where there's a wedge in there if you want. And so this thing is, of course, 1/2 fik dxi dxk. Okay. So this thing really is that, and we can write it as big DA, which might be a cute notation. And the question then would be, what else can you do with this? I don't know, but anyway, let's. All right, let me. We're almost at the end. Let me show you a different way of thinking about these things, which is something that people don't talk about very much, but may have a future in physics. I don't know. Well, the basic idea is to say psi prime A okay, so here we've got a transformation, and we can actually arrange for the action to be invariant even if this isn't even unitary, just as long as it's non-singular. All right, but if it is unitary, then what I'm about to say is kind of equivalent to the normal theory. So what we're going to do is we're going to define psi as a sum so where sum A equals 1 to n. In other words, if we're talking about SUN, then it would be n of these things. And this structure here itself will be invariant. By the way, let me just say something about forms that I skipped over. One of the nice things about form, one of the clever things about forms, is that they're intrinsically invariant structures. In other words, this thing here is invariant under general coordinate transformations because the dx mu goes one way, the a mu goes the other way under a general coordinate transformation. And just to make that explicit, maybe I should make this explicit rather than go on with this business. So in other words, A prime would be, now I'm talking about an arbitrary coordinate transformation. So A prime would be A prime at x prime dx mu, dx prime mu. Okay? All right. And first let's do the dx prime mu. That's the easy part. Dx prime mu is equal to, in other words, if x prime mu is x prime mu of some x's, then this thing is partial x prime mu, partial x, say, lambda, dx lambda. And then this one is the opposite. It is partial x, say, kappa partial x mu, a kappa of x. In other words, A prime mu of x prime is this. That's just the way a covariant field transforms. In other words, if it doesn't obey this, we don't let it in the paper. All right, and oh, there's a prime here. And now you see that this derivative couples with this, and what we all have here is simply partial x kappa, partial x lambda, a kappa of x. Notice this now is x, dx lambda. And then this, of course, is just a kappa of x dx kappa. So this one form is intrinsically invariant under general coordinate transit. Same thing happens for two forms and so forth. These forms are just intrinsically invariant structures. And the thing I like about this notation is that this thing is then intrinsically invariant. It's invariant at least if the e's transform the right way. And the right way for the e's to transform is EA prime of x is sum on B, EB of x, B inverse BA of x. And then you can see that the product of these two guys is going to be invariant. In other words, psi prime of x is going to be E prime A, psi prime A, and that is EB V inverse BA, BA C, psi C. And now this is just V inverse V, so this is just EB psi B, say. So this psi, it's kind of, it has that, the invariance property that was nice, one of the nice things about the forms. Now, the EA star dot EB, what's that? Well, it's not clear what that'll be, because these guys themselves are vectors. Okay, all these E's were vectors. That's so for that reason, this is an invariant vector. And now this thing is, say, E alpha star A, eta alpha beta, E beta B. I hope that this is just a typo in my notes and not a typo in my report. So I've just chosen to call eta the internal metric. That, in other words, what is the dot product of these vectors? And, you know, if we want to just go back to ordinary Yang-Mills theory for UN or SUN or one of the unitary groups or orthogonal groups, we just let eta be the identity matrix. But anyway, if we do that sum over alpha beta, what we have left is something that functions as kind of an internal metric, GAB. And we can use this GAB to raise an index, so we can say EA is GAB EB. And now we have EA dagger dot EB is delta AB. So now these things, so these vectors are the dual vectors of those vectors. And then the adjoint one dotted into the other will give you something that's just the delta, Kronecker delta. Now if we go back to Dirac's action, what we've got is gamma I bi plus m psi, but now I'm using the invariant quantity. So this thing is going to be psi A bar EA dagger gamma I bi plus m. Of course, these are normally written as Greek, but I think it's easier to read if it's Latin. And so what do we have here? What we have here is sidebar A. This is delta AB di plus EA dot EB comma I meaning the ith derivative. That is to say, this derivative hits that EB. Oh, I left out the mass term. All right, wait a minute, I left out the gammas also. And then this is just delta AB. Okay. And now you see what we've got is a generalization of the Dirac action of the Yang-Mills Dirac action. In other words, we've got psi bar A, gamma I, di AB plus m delta AB, psi B, and where this d ABI is delta AB DI plus AI AB, and AI AB is EA dagger dot EB comma I. Okay. For the unitary case, for unitary groups, orthogonal groups, you can forget about raising and lowering the internal indices. And in that case, you can just start out from the get-go with little n orthonormal vectors E, and this vector then is n orthonormal vectors times this, times the fields. But if you want to have something that's actually a Yang-Mills theory as opposed to just something trivial, then these vectors have to have more than little n components. And the reason is that these vectors then, if they're orthonormal, they're spanning some kind of a space, okay? And let's say you have two of them. In fact, if this were SU2, you would have two of them. Okay, so you have two of them. But if they're in a two space, well then all you've got is two orthogonal vectors in a two space, and you can't get any curvature. So you need to have them to be two orthogonal vectors in a space that's 3, 4, or 5 dimension, so that, in other words, you can't have this thing curved unless you can bend it into a third dimension. So that's how you get the curvature. All right. And in particular, if we restrict ourselves to the case where everything is, where these are orthonormal, so we're talking about unitary symmetries, then this action here, so the unitary case, then you can lower this A, it's still orthogonal, and so this thing is simply psi bar A gamma I delta AB DI plus EA dagger dot EB comma mu plus M delta AB psi B. And so this is exactly the Yang-Mills Dirac action. when these things are orthonormal for a unitary group. Two Indian mathematicians showed that you could represent arbitrary unitary groups, or the connections for arbitrary unitary groups in this way, as long as these vectors, for SU2, as long as they had more than two, not only more than two, but more than a certain number, and they gave a lower bound for how many components you need. And it's still an open question in mathematics what the minimum number of components is in order to represent the arbitrary connection. And then one question that's occurred to me is, suppose you actually took this as, and so let's forget about the non-compact groups, but instead just look at the unitary groups. You could imagine doing the functional integrals with these, in this notation, with these invariant vectors and these vectors E, these orthonormal vectors, n orthonormal vectors, but of arbitrary, of an uncertain length, at least at this stage uncertain. The question is, would your functional integral and your physics, would you get a different QCD, a different strong interaction theory, as you've made these vectors longer and longer? I don't know. Probably. And then the question is, would confinement show up in a natural way at some length? I don't know. Okay, I have more to say about this, but I think I should skip that and now just say a few more things about group theory. We've got only 5 minutes left anyway. So let me the basic insight of Lie was, this is not T.D. Lie, this is L.I.E., was to represent groups basically by the exponential notation. So in other words, we can say D of alpha is E to the I alpha, what do they call this? Alpha ATA. So these are, if we're talking about unitary groups, let's just stay with unitary groups for a moment, but this actually is a general representation for arbitrary, well, maybe not symplectic, but arbitrary compact or non-compact. Forget symplectic for the moment. I always have to rethink symplectic. If the TA is a Hermitian, then this thing is unitary, clearly. And the reason for that, just in case it isn't all that clear, is that d alpha dagger would be e to the minus I. The alphas are real, but if these are Hermitian, then it's e to the minus I, A alpha, T alpha, and this is clearly the inverse of that. So basically the idea of this representation is that for a given n vector, little n vector, in other words, 2 vector for SU2, 3 vector for SU3, of real alphas, you get a particular, well actually no, you get, for SU3 it's an 8 vector, sorry. For SU2, actually it's a 3 vector. So I was wrong over here when I said you only had 2 E's for SU2, you have 3. Well, now I'm starting to get completely confused. There are 2 different N's. There are certainly, I mean for SU2 you certainly have 2 B's here. Yeah, well, I'm thinking of different things here. I was right when I said 2 for SU2, 3 for SU3 there. But here, the A is 3 for SU2 and 8 for SU3. That's how many generators there are. Now, what you can do is you can, so a representation is a map from the abstract group into matrices, and one convenient way of doing that is this. And now if you imagine having e to the I epsilon, say, TB, e to the I epsilon TA, e to the minus I epsilon TB, e to the minus I epsilon TA. It turns out that this is actually e to the epsilon squared, the commutator of TA with TB. And this is true whether it's compact or non-compact. So that's just arithmetic. On the other hand, it's also true that if you just multiply these out, this has got to be something of the form e to the I epsilon squared, some linear combination of the generators with an epsilon squared. And so what we get is that necessarily the commutator of two generators is I at CAB TB. And this is true whether it's compact or non-compact.
Not TC?
Huh?
Not TC?
Sorry.
Long throw.
Whoa! Good catch. All right. These things are called the structure constants. And the structure constants are the same for all representations. And the reason for that is, if you had another representation, what does the representation have to do? The representation has to respect the multiplication law. So if you do this for a different representation, you get the same result with the same f's. And so the f's have to be the same no matter what the representation is. Okay, we're basically out of time, but maybe somebody has a question. No pang of hunger out there?
Well, that S for
Hold on, let me get the handy.
well, that S for SUN, that means special, right?
The S?
The S in front of the, yeah, the S means special, right?
Yes. At least
Because it has determinant.
At least that's what people in America think. What the Germans think, I don't know. But it means determinative U is 1.
Okay, because it could, because otherwise it could be -1, but that's for the special case where it equals 1. Okay, yeah.
Well, if you had a unitary matrix, the determinant could be an arbitrary phase. In fact, what typically is true is that UN, in other words, you can think of UN as U1 times SUN. And that's why you see SU3 has 8 generators, because U3 has 9. And the reason is that U3, you've got 1, 2, 3, 4, 5, 6, 7, 8, 9 arbitrary numbers, so you need 9 generators. But there's one generator that's just 1, 1, 1. In other words, just the identity times some arbitrary number. That generator, well, not really arbitrary, but some number, that thing generates U1. So you can always, from UN, you can write it as U1 times SUN. And so for U2, the group, not the band, for U2 is U1 times SU2. This has 3 generator, that has 1. U3 is U1 times SU3. This has 8 generators, this has 1. You can always pull out a U1. And the problem with U1s is in physics they often give rise to things called anomalies. And by the way, there's a story associated with anomalies. There was a guy doing a thesis, I think his name actually was Schwartz, but a different Schwartz, maybe the father of this Schwartz. Anyway, at Columbia, and he started working on this problem, a U1 theory, and was computing, I think, the decay of the pion. And he kept getting results that were sort of conflicting. And finally turned out that he had discovered the U1 anomaly. And he then said, well, if theoretical physics has things like this floating around, I'm getting out. He went into experimental physics. I think he won the Nobel Prize, but I'm not sure. But anyway, he's presently in experiment, probably at CERN at this moment, waiting for the LHC to change. All right, we might as well end this thing.